Picking up where we left off on the last video, we were trying to determine the surface area of a sphere. We were given the equation in that example, and of course it looked like our radius was just in general in A, but we've worked out the formula for the area of the surface area with the double integral of the magnitude of the partial derivatives cross product. And you can see we're almost done. We've arrived at this double integral, but of course we can separate these integrals into two distinct ones, one in terms of theta, the other in terms of phi. And continuing up our work here as we evaluate the first integral, integrating with respect to theta, the antiderivative of a would be a theta, and of course we'll work that out between 0 and 2 pi. Also, we're going to take an antiderivative of sine of phi, which would be the opposite of the cosine of phi, and we will evaluate that between pi and 0. Well, finishing this up, substituting this in, I hope you could see very quickly that this first integral would arrive at 2 pi. Second integral is just a little bit more involved. Negative cosine of pi minus negative cosine of 0. But the cosine of pi is -1, so we'd have a negative -1, which would become positive 1. Minus a negative would turn into plus a positive, and the cosine of 0 would be a 1. So 1 plus 1 is 2. And forgive me, I forgot an a for this first integral here. So we have 2 pi a. Really multiplying that to 2. What do we get? 4 pi. And forgive me, I actually forgot the square there. A squared. Made a couple mistakes there, copy mistakes. So as we finish this up, you'd see that your surface area is 4 pi a squared. And back in geometry, one of the earliest things you learn about a sphere is that its surface area is 4 pi r squared. Since r is going to be designated as a here, we see that really is right in line with what you've learned in the past. Okay, the surface area, when you have the graph of a function, very often you won't have the benefit of being given a specific parametric equations. Maybe you won't have the benefit of quickly being able to convert to polar or to spherical coordinates like we did in the last problem. Very often our equations might be in terms of x, y, and z. And what we saw in the previous lesson is that great parametrization that you can have if you have an equation with x, y, and z is really just the very simple form of letting x be a parameter, letting y be a parameter, and then letting z be a function of x and y, and letting z equal that function, solving for z uniquely. So what we would see very quickly is that r would be in terms of x and y, and it would look very simply as x times vector I plus y times vector j, and then we'd have z, whatever z is equal to. That's f of x comma y. That would be your k component. Well, take your partial derivative with respect to x. You can see that you'd be left with 1i. The j component completely disappears. And then you'd have to take a partial derivative of f with respect to x. That's what we're coming up with right here. That's your k component. Similarly, if we went back up over to our original parametric equation, if we took our derivative with respect to y, the I component would drop out. The derivative of y is just a 1, and then we would be left with the partial derivative of f with respect to y times vector k. So what we have here is the two partial derivatives. Of course, we would very much like to evaluate their cross product. So let's do that quickly. We have I, j, and k. Writing this form out, this would be x, this would be y, and here we could say here's f. Pardon me. Actually, forgive me. We've got r sub x. That's this derivative right here. It'd be 1i plus 0j, and this would be the partial derivative of f with respect to x. Then for y, r sub y, that's what we've highlighted in turquoise, that's 0i plus 1j, and my k component is partial derivative of f with respect to y. Now, working this determinant out by hand, you could see what we could do very, very quickly. You could see crossing out the I column in the top row, doing a 2 by 2 determinant. The first diagonal would wipe out entirely. You'd be left with the negative partial derivative of f with respect to x. That's your I component. Well, then what? Then we'd immediately jump over to our j, and we could say, well, remember we'd say minus, but notice that we'd have, for our first diagonal, we'd have partial derivative of f with respect to y, minus 0 times the partial derivative of f with respect to x. So that's all you're left with. Take a look at what happens with your k. Very nicely, this first diagonal is just a 1. Minus a 0, so it's just a 1 itself. So my goodness, this is the cross product of r sub x by r sub y. By the way, that's not the only time you're going to see this in this chapter. It's actually worth remembering and memorizing. If we were to find the magnitude of that, we could find the Pythagorean theorem in 3-space, squaring each of these components. You would have partial derivative of f with respect to x, squaring that, plus partial derivative of f with respect to y. Now I'm getting rid of the negative. The negatives, of course, are going to cancel out. And this would be your partial derivative of r sub x times r sub y cross-producted, taking that magnitude. Look, the author very quickly points out that this is a convenient surface area formula. Of course, what you saw earlier is that, yeah, you'd have r sub x cross r sub y in its magnitude here. But this formula shows up so very much. The only difference is the author put the 1 out in front. It's well worth memorizing this. You definitely don't want to have to rederive this all the time. So this is a surface area formula, most notably when we have equations of the form z equals something. Notice what's happening. We don't have a vector type of equation in parametric form. This is more typical. This is honestly what we see more likely. So let's say that you were asked to find the surface area of a paraboloid, z equals x squared plus y squared, and it lies under the plane z equals 9. So what you could do super quickly is realize that this graph is a 3-dimensional parabola. Okay, it's like looking at like a shape like so, and z equals 9 would be a plane covering the top. So we'd have this, it's not a cone, but it's like, imagine we've got this piece of paper in this paraboloid shape, and we're under this value of z equals 9, and we'd like to find out what the surface area is. Well, my goodness, what you can do is just follow this formula. The partial derivative of z with respect to x, I hope you can see, is 2x. The partial derivative of z with respect to y is simply 2y. So where are we going with this? Well, according to this formula that we see here, the surface area of this solid would be the double integral of 1 plus, and then we'll have our 2x squared plus 2y squared, and then it's dA. I do want to point out something very, very important. This is our double integral is going to have to be evaluated much the same way we did earlier in the year. We don't have the benefit in this regard when we're working with functions to have quick substitutions for our parameters. Like in that last problem with the sphere, we knew that phi went between 0 and pi, and theta went between 0 and 2 pi. Very often what you have to do is just go back to how we worked this out in the past. Now, I'll be honest with you, as we're looking at this, we need to realize that when you saw a problem like this long ago, a number of months ago, what you would see is that with z equaling 9, we could quickly say that in this equation of z equals x squared plus y squared, we have 9 is equal to x squared plus y squared. So up on top, we would have a circle where z is equal to 9. We'd have a circle with a radius of 3. But what we did long ago for these double integral problems is we realized that we were making rectangles, rectangular prisms, in fact, off of part of the xy plane. We would build them up. And of course we had to pay very specific attention. We'd be building these rectangular prisms down below the solid. The largest outline of this solid would be this circle, x squared plus y squared equals 9. So this is where we would be creating our prisms. Now ordinarily we could also think of this as a type 1 or a type 2 region. There are times when we absolutely must do that. There's some problems in the homework where they force you to do that. But when you have circles, you do have a delightful shortcut in regards to polars. And with polars, my goodness, that's something you want to take advantage of every single time you can. Look, we have, by factoring out a 4 inside the square root, we just have x squared plus y squared, and that would lead us to, very quickly, x squared plus y squared is r squared. Now, when we are converting to polar, we should remember that our dy dx would be replaced as an r dr d theta. R dr d theta. Very important for us to remember that. We showed and proved that that was the case even with the Jacobian. But then, of course, we'd have to pay attention to the boundaries of R. Well, again, this, I can't stress enough, is coming from this circular region on the xy plane. That's where we are creating our rectangular prisms. And you could see that in a polar form, our radius would span from 0 out to 3. Remember, x squared plus y squared equals 9 is a circle with a radius of 3. But we want everything from the origin out there, not just the rim of that circle. For theta, of course, we're just going to integrate between 0 and 2 pi. From here, what we could do is quickly do a u substitution if you'd like. However, for the sake of time, we could even refer to the graphing calculator and arrive at this value. Now this value would be the surface area of that solid. And in other words, it would let you know how many square units of paper it would require for us to make a paraboloid that would go up to z equals 9. So I hope this is helping. We're going to be picking up on a very important topic tomorrow and the next day, something on surface integrals. Lots of applications to electricity, magnetism, and fluid dynamics. Well, best of luck to you.